derivation of surface integrals, which are related to finding the area of a surface. And you're already familiar with finding surface area. And but for that one, we did solids of revolution. In this case, we're not doing solids of revolution. In this case, we are finding areas of surfaces. In this case, like paraboloids or any other spheres, for example. And so we did a derivation of the generalized version of a surface area. And one thing I would like to point out is that just same way we did it with air, for example, with the double integral dA. What does that double integral represent when we have a 1 over here? Area. What about the double integral when we have some f of x y over here? What does that represent? Volume. What does the triple integral with a 1 dV represent? Volume, right? So in a similar way, notice we have this surface area with a 1 in the integrand. So, that's the surface integral. So whenever we have a 1 in the integrand, that is, that 1, it's still multiplying over here. That's going to give us the surface area of the solid, well, depending on the boundaries and the like, all that stuff, right? Whenever we have something different, that's going to be the most generalized form of a surface integral, and that's going to be something more like a density function, if we will. So in this case, we will be finding the mass by adding these areas, right? The mass of the surface in this case, and we will get to see that. In the meantime, let's look at some examples finding some surface area. So find the surface area of the part of the surface z equals to x squared plus 2y that lies above the triangular region T in the xy plane with vertices 0, 0, 2, 0, and 2, 1. Again, first thing we do is graph. But again, most of the times what we graph is the projection in 2D. In pretty much the only one case that we're able to graph in 3D is the plane that it gives us like a tetrahedron, right? And when it comes to parabolas and other things, it's kind of hard to do. But in this case, it's fine. It's going to be a triangle in the xy plane with the points 0, 0, 0, 0, 2, 0, and 2, 1. All right. So that's our triangle here. And so what are we going to need to find the surface area? Well, notice we're given a surface Z, which is actually our f of x, y. Again, it's different notations, right? Z or f of x, y, or f of x, y, z, depending on what we're given, right? So we need to find the partials of f with respect x and with respect y. So let's go ahead and do that. Let me finish drawing the region. So we're going to have some solid with a triangular base. That's what we are finding essentially. So this line right here, let me take the partials first. dz dx, so the partial with respect x equals to 2x, and the partial with respect y equals to 2, okay? So if we set up the surface area integral over the region T, ds, be careful because this time this s is uppercase, lowercase is for line integrals, all right? So big S is surface area for surfaces in general. So double integral over T of the square root of the partial of z with respect to x, quantity squared, plus the partial of z with respect to y, quantity squared, plus 1, and that dA. Where the dA, it's going to be either dy dx or dx dy, depending on whether it's more convenient due to the region being horizontally simple or vertically simple. All right? Well, so let's just substitute the derivatives, the partial derivatives, and I'm going to leave some space for the bounds already. So that's the square root of the partial with respect to x, that's 2x, quantity squared, plus the derivative of with respect to y, which is 2 quantity squared plus 1. And simplifying this radicand, I'm going to do, well, let's do dA for now, over t. And, well, so that's the double integral. Yes, I'm going to leave the space finally for bound. So that's going to give us a 4x squared. And 2 squared, which is 4 plus 1, that's a plus 5. dy dx. And well, now let's find out the limit. That's where we are going to iterate the integral. We're going to go the dy dx or dx dy. I think dy dx is more convenient. We can find the equation of this line, which passes through the origin 0, 0, and the point 2, 1. It has a slope of 1/2, in fact, so that's y equals 1/2 x plus essentially 0 because it passes through the origin, but we don't need to write that 0. So the limits of integration will be, well, in the y direction, it's going to go from 0 to 1/2 x, and in the y direction from 0 to 2. And evaluating this integral, well, let me do the first step. The integral from 0 to 2, the integral from 0 to 1/2 x. That's the integral with respect to y. That's going to be simply y square root of 4x squared plus 5 evaluated from 0 to 1/2 x dx, which in this case, well, using fundamental theorem of calculus, one time that's going to give us the usual upper minus lower. So that's the integral from 0 to 2 of 1/2 x square root of 4x squared plus 5 dx. And well, if you observe this integral, pattern recognition, we have 1 degree higher, 1 degree lower. U substitution would be great, but I'm going to skip that U substitution. I mean, let's just go with the final answer. It's going to be a wacky one. It's going to be 1 over 24, 21 to the 3/2 minus 5 to the 3/2. All right. I think I have discussed numbers like this before, in which, well, the denominator of the rational exponent essentially tells us the index of the radical, all right? And if we change this back to radical notation, we wouldn't be able to find or to compute perfect squares because neither 21 or 5 are perfect squares. And well, just in case my MATLAB doesn't accept rational exponents as final answers, I'm going to go back to radicals for a second. And that's going to be the square root of 21 cubed minus the square root of 5 cubed. And simplifying or playing with the powers, that's 1 over 24. That's square root of 21 squared times 21 minus square root of 5 squared times 5. And only this way we can simplify some perfect squares, but we will still be left with radical factors. So that's 1 over 24. That's 21 root of 21 minus 5 root of 5. And that's our final answer. So I discussed this part just in case my MATLAB doesn't accept this rational exponent, right? It's going to take us back to basic properties of radicals in the end, okay? So, example number 2. Another surface, another calculation of a surface. By the way, this is what we're doing in this case is finding the upper surface, so the surface that lies above the solid, because we're going to get into other integrals, the flux integrals, in which we are going to calculate the surface involved. It's not going to be just the upper surface, but also the bottom surface, or depending on the kind of solid that we work on, right? You'll see. Well, in the meantime, let's look at another example of this. So set up but do not integrate a double integral to find the upper surface area of the plane 2x plus 4y plus 3c equals to 24 in the first octant. Well, so here is where we will draw this in 3D. This one is it's okay to draw. And so let's see. And again, recall that we can draw get this tetrahedron by getting the x, y, and z intercept. So the x-intercept make the other two variables y and z equal to 0. That's essentially 2x equals to 24. That's a 12. And the y-intercept make x and z equal to 0. 24 over 4. That's going to give us a 6 over here. And for the z, make this to 0. That's 24 over 3. That's an 8. All right. And that's going to give us the following surface. So we're going to find this area of this plane right here. All right, this portion of the ball. Recall this plane actually spans forever, infinitely. All right, to the infinite. In this case, well, we just want the portion of the plane that lies in the first octant. So number one, okay, so we're given a function z in this guy. Well, because we're given the equation of the plane in standard form, so we need to make it a function z. So that is, I'm going to solve for z, so 3z equals to 24 minus 2x plus 3z, minus 4y. That's so we can find the partial derivative that we need. So that's 24 over 3, that's 8, minus 2/3 x minus 4/3 y. And I think you can see why they're asking us to just set it up, because the numbers are not going to be that pretty. All right. So, not yet. So let's find the partial derivatives. Partial of z with respect x, that's a negative 2/3, and partial derivative of z with respect to y, that's negative 4/3. All right, and let's set up the surface integral. That's surface area equals the double integral over r over the region r ds, and that's the double integral over r of the square root of the partial with respect x quantity squared plus the partial of z with respect y quantity squared plus 1. And that dA for now. We will take care of the iteration in a second once we substitute, and then because we still have to have a look at the projection in the xy plane so we can see the bounds dy dx. Okay, so let's see. Our partials, well, number one, so that's double integral over r, that's the square root of negative 2/3 quantity squared plus negative 4/3 quantity squared dA. And simplifying the radicand, so that's 2 squared, which is 4, and then 4 that's a 16 plus 4, is that a 20? Oh, I'm missing a 1, right? I'm missing a 1. That's true. Yes, dA. Thank you. So that's the double integral of r of the number. So after simplifying this, we should get 29 over 9 dA. So now let's iterate. Let's find the limits of integration. So that's the square root of 29 over 9 dA. And in this case, let's see what's going on. So we're going to look at the projection in the xy plane, right? So that is what's going on over here. And for that, I'm going to take that part and I'm going to draw it here. And that should be this line. And that goes to 12 and 6. And in this case, well, let me honor the colors again. Shade of purple here. And well, what's that equation? Well, so we can see it's a linear equation. It's a straight line with a y-intercept at 6, so plus 6. And well, the slope is, well, dive 6 units, around 12 units. That's essentially negative 1/2. Negative 1/2 x plus 6. And we got everything we need. And well, so in this case, y varies between 0 and 1/2 x, or rather negative 1/2 x plus 6, and x varies between 0 and 12. So in this case, they were just asking us to set up the integral. I guess some question like this would be giving you on the final exam, if any, you know, something, nothing really crazy, easy numbers, and still just set it up, all right? All right. Let's look at one more question before moving on to the next topic. Yes.
The denominator, wouldn't it be 3?
Yes, that'll be 3. Yes, I don't know what was I thinking. Yes, thank you. So yes, in this case, I was supposed to evaluate at least the perfect square. Well, the 29 is not a perfect one, all right? So, example number 3, find the surface area of the part of the paraboloid z equals to x squared plus y squared that lies under the plane z equals to 9. So in this case, careful, because it's not the xy plane as usual, for which we look at the projection, set them together. It's going to look a little different this time. You'll see. So, well, I'll try my best to draw a paraboloid here. So, it's going to be like this. And paraboloid, it's going to look like this, I guess, right? So. And in this case, well, the plane z equals to 9. All right, it's a horizontal plane. Z equals to 9, sort of. All right. Well, so number 1, what's going on in the 2D projection? Well, so in this case, the 2D projection would be by setting the plane, right? Plane equal to the paraboloid. That is the equation of the plane, which is x squared plus y squared, and equals to 9. Essentially, the z of the plane equals the z of the plane. So that's how we're going to get the intersection. And from here, we can recognize that this is the equation of a circle over with a radius of 3. So that's what we're going to do in the xy plane projection. Well, so that's telling us that, well, not yet. Let's set up the integral first. So what do we have? We have our z here. How about we take the partial derivative, partial of z with respect x, equal to 2x, and the partial of z with respect y equals to 2y. So surface area equal to the double integral over the region R ds. That's the element of surface area. And well, double over R, that's the square root of 2x quantity squared plus 2y quantity squared, and I'm not going to forget about that one again, all right? ds. Oh, wait, not ds. Let's call it dA now. Once we introduce this radical symbol, we change that with a dA, okay? So because that's what's next essentially is to iterate the integral, which, well, we're almost there. So that's going to be the double integral still over r. Let's simplify the radicand first. That's going to be 4x squared plus 4y squared plus 1 dy dx. And well, so here is where we are going to iterate the integral. Oh, not yet. Let me factor something out first. Almost there. So let me factor out the 4x squared plus y squared plus 1 dy dx. So if we were to evaluate this integral as is, well, check how y varies between that radical function of the upper semicircle minus the lower semicircle, which will be really, really bad to evaluate. And even if we did it, even if we take this direction, okay, try to set up the method to evaluate with respect to y. Well, notice we don't have a power of y that could help us set the u du part of the problem. So we cannot use the u substitution in this situation. So we would have to use maybe trigonometric substitution. And well, it would be interesting to do a trigonometric substitution with two variables. Well, just hold the other two constants. That's fine. But we have better tools to do this a lot quicker. Do you see? Yes, Derek?
RD theta.
Right, because in this case we are integrating over a circular region that's screaming for polar. All right? Do it in polar. Well, this is the circle of radius 3. Essentially, our radius is varying between 0 and 3. And well, because in this case we want the whole circle, theta is varying between 0 and 2 pi. All right? So it's going to be a lot easier to do that rather than trig substitution with two variables. It would be interesting though. But I mean, just take advantage of the tools that we have. So double integrals 0 to 2 pi, 0 to 3, and that's the square root of 4x squared plus y squared, which is r squared plus 1, and dy dx becomes r dr d theta. And converting this into polar coordinates, you see how this time we have that power of r, which is 1 degree less than what we have inside of the radical, which would work very well for a u du substitution. All right, so, but well, after evaluating this integral, you should get 1/6 37 to the 3/2 minus 1 pi. And again, let me just work out this number just in case my MATLAB doesn't like this rational exponents. That's 1/6. That's the square root of 37 cubed minus 1 pi, which is 1/6 37 root of 37 minus 1 pi. Okay? So that's another example for finding a surface area. All right. So that's the surface area of the part of the cone that lies below that plane. So we have a limit above this time, not like the other type of questions that we have done before. We have the upper hemisphere with the xy plane being the lower bound, or a parabola with the same xy plane being the lower bound. Now this is upside down. All right. Okay. Surface integrals. So in general, so again, so now we're going to move on to those integrals that we are not going to have a 1 in the integrand anymore. So as a way of a summary, I mean, we have evaluated integrals over an interval. That's half one. Integral of f of x between a and b, all right? And then we have evaluated integrals over a region. That's the double integrals, in which we look, yes, to the shape, you know, and we determine the usual vertically simple, horizontally simple. Those are over regions. And then we have found integrals over a volume and then over a curve, which are the line integrals. So we move on to a new kind of integral, which is the surface integral. So we learn how to compute the upper surface, which is what we did, the upper surface area of a solid. But a surface integral, it's an extension in which, in this case, we are going to integrate with respect some surface area. And, well, this f of x, y, z, which, by the way, the z gets replaced. Here is the little trick here. Whatever you see the letter c, the letter z, replaced with the given function that depends on x, y, because this dA just depends on two variables. We don't have a triple integral that contains the three variables. We don't have a double integral, so this is going to be a dA, which is dy dx. So everything containing a z, replace it with whatever function given in terms of x and y. All right? So that's really the real trick. And again, this function f of x, y, z, which is really g of x of y, could be a density function. And well, in this case, we would be finding the mass of that surface, all right? And in fact, well, one of the examples is to find the mass of a cone. You'll see that one later. In the meantime, well, let's see. How about we look at one example and evaluate the surface integral. Notice the presentation of this surface integral. We no longer have just the double integral symbol and the ds. We have now a function of f of x, y, and z, which again will be replaced with the usual, right? Well, so in this case, we evaluate the surface integral where the region S is the plane z equals to 2 and the circle and the unit circle, all right? So let's see what this is about. Okay, so I mean, if we were thinking of this as a triple integral, it looks like a cylinder, but in this case, well, it's not a triple integral. So again, well, you'll see how we're going to go about this one. So we have a function z in this case, and be careful because this f of x, y, z, it's not going to be the z function for which we will take the partial derivatives. In fact, it's a little weird, but the function we're going to take those partials is just this z equal to 2. So partial of z with respect x, well, it's just constant, so that's a 0. Partial of z with respect y, that's also 0. And well, let's plot the region over which we're integrating. So that's the unit circle. And that's the unit circle, and let's work with the integral now. So what do we have? That's the double integral of x minus 2y plus z and ds. But this ds, again, we're going to replace it with the element of surface area. In this case, that is, this ds becomes this whole madness right here. All right. And well, just to be clear about it, I mean, this z, this is also the same as saying z with respect x and z with respect y. That depends on the notation. So I used the Jacobian notation in this case because I was using the letter g. But this g, again, recall that it's only a function of two variables, which it's actually here in the picture. Z is just a function of two variables, not a function of three variables. All right, so let's rewrite the surface integral over S. That's x plus 2y, x minus 2y plus z. Instead of the s, that's the square root of the partial of x with respect to x, quantity squared, the partial of z with respect to y, quantity squared plus 1, dA. And well, so that's the double integral over the region S, over the surface. Well, actually, that's going to be the region R this time, because now that we introduce the dA, that becomes an R, in fact. All right? So that's x minus 2y plus z, and that's the square root of, well, essentially 0 squared plus 0 squared plus 1. That's simply the square root of 1, isn't it? Which is just 1, which we don't need to write in there. So we're going to be left with the double integral and over R, x minus 2y plus z. All right? However, one thing to be careful here, notice dA is essentially, okay, I mean, this is essentially dy dx. So we need to have our integrand only in terms of y and x. Here we have x, y, and we have z. So we need to replace that z with whatever function we have. Well, in this case, how about we replace that with 2, all right? That's the only little pitfall that we need to be aware when it comes to surface integrals. So I don't think there's other pitfalls with other. I mean, there's pitfalls with the other kinds of integrals, you know. So we did the setup, the region, and whatever. Substitute, evaluate. But in this case, just be careful with the z's, right? So, so that's the double integral over R of x minus 2y plus 2 dA. And well, in this case, notice the region over which we are integrating is circular. What would be a good way to evaluate this integral? Polar, right? Because I mean, essentially this would be root of 1 minus x squared, and this would be negative root of 1 minus x squared. Do you want these limits here? Negative root, positive root, from negative 1 to 1. Do you want to evaluate such an integral? Not really, right? So let's take advantage of polar coordinates. And well, let's replace x with its equivalent in polar coordinates. What's that? R cosine. And minus 2 r sine, and just plus 2. dA becomes dr d theta. Am I missing something? R, right? So that goes from, well, in this case we want the whole circle, 0 to 2 pi. Well, actually first the radius, and 0 to 1, and 0 to 2 pi, right? And well, so evaluating this integral should give us a 2 pi. All right? Yep. So again, let me just write down below this curve right here. R is varying between 0 and 1, and theta is varying between 0 and 2 pi. I forgot to write this down when I was setting the region, but again, my advice is to always write that down next to that region, next to the projection in 2D, so you can easily see the limits of integration before setting up the integral. All right? And